Hello, my name is Hans Burgerhoff and I work as a statistician in the UMCG. This video is part of a series of videos about medical statistics. In this video, I would like to tell you something about descriptive statistics. Imagine you're one of the authors of this article about the effect of ovarian hyperstimulation on the blood pressure of 4-year-old IVF offspring. You made observations on several variables in a sample of 194 children. How would you present and summarize the observations on, for example, the blood pressure of the children, the weights of the mothers, or the variable gender? The authors gave information in tables like this, grouped on the basis of the type of IVF. 2 IVF groups and 1 group with naturally conceived babies from subfertile women. For some variables, the authors used mean and standard deviation to describe the observations in each subgroup. For other variables, numbers and percentages, or medians and ranges. What are these measures exactly? How did the researchers decide which summary measure to use for each variable? Well, there are several types of variables. The main division into types of variables is between numerical or quantitative variables on the one hand and categorical or qualitative variables on the other. A numerical variable can be either continuous, like height, or it can be discrete, like number of children in a household. For a continuous variable, there is no indivisible unit. You can measure in meters, centimeters, millimeters. For a discrete variable, such an indivisible unit exists. You can have 0, 1, 2, 3, etc. children. In this case, the indivisible unit is a child. A categorical variable can be either ordinal or nominal. An example of an ordinal variable is degree of pain. There is a clear logical ordering. If there is no logical ordering, the variable is nominal, for example, marital status. The categories are single, married, widowed, divorced. This is an arbitrary order. A categorical variable with only 2 categories, like presence of a disease, yes or no, is called a binary or dichotomous variable. Here we see an overview over the types of variables and the way we can describe them, either in a numerical way or graphically. If we have a continuous variable like height, we can show the distribution of the data in a histogram. In a histogram, the observations of a continuous variable are grouped into classes, and the frequency of the observations of the classes are shown. If the shape of the distribution is close to the form of the bell-shaped normal distribution, also known as Gaussian distribution, we can use the mean to describe the location of the distribution. This mean, or to be more specific, the unweighted arithmetic mean, is defined as the sum of all observations of the variable x divided by the number of observations. In a formula, x bar equals capital sigma, meaning the sum, of all observations xi divided by n, in which n is the number of observations. I think this formula is quite straightforward. Now let's have a look at the continuous variable BMI of the mother. As you probably know, this is defined as the weight in kilograms divided by the square of height in meters. In this dataset, the distribution is skewed, and the mean is not a good measure for location, because it will be influenced by the extreme values. A better measure will be the median, which is defined as the mid of the ordered observations. I will give 2 examples how to calculate the median. If we have an odd number of observations, for example 5, we start by ordering the observations. 10 is the smallest, then 15, 16, 28, and 30. The median is the middle of the ranked observations. It's the observation with rank number n plus 1 divided by 2. In this case, we have 5 observations. 6 divided by 2 is 3. So we pick the third observation. In this case, the median is 16. If we have an even number of observations, for example 6, there will be no observation in the middle. Again, we start by ranking the observations. Now the median is defined as the mean of the two midmost ranked observations. In this case, 16 plus 28 equals 44 divided by 2 is 22. In fact, the median is a special case of a percentile. Percentiles are values giving relative positions in a distribution. A percentile px is a value with x% of the distribution on the left-hand side of it. For example, the p5 is the value below which 5% of the observations are located. In the case of the BMIs of the mothers, the p5 equals 18.2. Telling us that 5% of the mothers had a BMI smaller than or equal to 18.2. The median, the observation in the middle, is by definition equal to the p50. Here is the formula to calculate a percentile. More information can be found in section 3.3 of Kirkwood and Stern. A very useful graph for continuous variables is the box plot, especially if you want to show the distribution of a continuous variable within subgroups. In this box plot, the 3 IVF groups are shown with respect to the birth weights of the children. More information about this graph can be found in Kirkwood and Stern. For qualitative data, we can calculate the median as a measure for location only if the variable is ordinal. For nominal variables, without a logical order, we can only use the mode as measure for location. The mode is the category with the highest frequency of observations. This can be shown graphically in a bar graph. Here we see a bar graph of the number of children in the 3 IVF groups. The sub-NC group is the mode. If you want to show a subdivision, you can do so using clustered or stacked bar graphs. In this case, we show the distribution of boys and girls within the IVF groups. Now, location is only one feature of a distribution. Dispersion or variation is another one. In this population of female soldiers, there is not much variation in height. In the Dalton family, there is. Now we would like to quantify the dispersion. Here we see the distribution of the variable BMI of the mothers again, together with a table of descriptives from SPSS. There are several measures for dispersion. The most simple one is the range, which is defined as the difference between the highest and the lowest observation. A drawback of this simple measure is that one single outlier has great impact on the range. The range has been calculated as 31.2 now. But if the extreme value of 46.68 were no part of the sample, the range would have been much smaller. A measure for dispersion which is less sensitive to outliers than the range is the IQR, the interquartile range. The first quartile is the value with 25% on the left-hand side, so it's equal to the P25. The EQR is defined as the difference between the third and the first quartile, and is used for skewed distributions. Now we would like to have a measure of variation based on all observations. Say we have a family with 3 children. All 3 of them get pocket money every week. The youngest gets 3 euros, the oldest gets 17 euros, and the third child gets 7 euros per week. We are interested in a measure of variation. The range is 17 minus 3 equals 14 euros. As you can see, the range depends only on the minimum and the maximum. It does not matter what the third child gets. We will calculate a measure of dispersion involving all observations by focusing on the deviations. The deviation of an observation is defined as the observation itself minus the mean. It's easy to calculate in this case that the mean pocket money equals 9 euros per week. So in this example, the deviations are minus 6, minus 2, and plus 8. Is it possible to use the mean deviation as a measure of variation? The answer is no. Why? Well, let's calculate the mean deviation. Minus 6 minus 2 is minus 8, plus 8 is 0. The mean deviation will always be 0 by definition. A possible solution could be to take the mean of the absolute value of the deviations. But it's more common to make all deviations positive by squaring them. The variance is defined as the sum of all square deviations divided by n minus 1. Maybe you wonder why we divide by n minus 1 instead of by n. There is a good mathematical reason for it. You can prove that the estimate will be unbiased in this way, but I will not give you the proof of that. In this case, the variance equals 52. But 52 what? This is a mean of squared euros. So the variance has a different unit than the unit of the observations, which was in euros. To overcome this problem, the most commonly used measure of variation, the so-called standard deviation, is defined as the square root of the variance. In our example, standard deviation equals the square root of 52, and that's almost 7.2. This is in euros, and it's an estimate for the mean distance of the observations to the mean. In a formula, the standard deviation is given like this. Ending this video, I will show you some features of SPSS. Here we see a data matrix in SPSS. In the top of the window, you see the menu, with a lot of possible commands. In the columns, you see the variables, like patient number, groups, gender, etc. In the rows, the cases or respondents are shown. At the bottom of this window, you can see we are in the data view mode. If you check on variable view, you go to this window, showing details about the variables like type of variable, variable labels, and value labels. For example, the categorical variable with the name breastfeed has variable label breastfeeding and values 0 with label less than 6 weeks and value 1 with label 6 weeks or more. The SPSS menu has a pull-down structure. Checking the option data, you can do operations on your data file like splitting the file in groups or selecting groups of cases. Checking transform will offer you a lot of options to recode your variables or compute new variables. Analyze gives you access to all kinds of statistical analyses, both descriptive statistics to make frequency tables, calculate means, standard deviations, and so on, as inferential statistics like t-tests, correlation, and regression models. For graphical output, you can choose graphs and legacy dialogues. Whatever option you take, you will always get in a dialog window. And by filling in the required information and checking OK, you will get the results in an SPSS output file. Well, so much for descriptive statistics. Make the exercises of video 2, check your answers, and continue with the next video about probability theory. I wish you good luck.